Good morning and welcome back once again to this second lecture, especially about the review of Sobolev spaces. So, in the last part of the last talk, we said we will discuss 3 to 4 issues about the Sobolev spaces. These are all deeper studied, so you have to spend substantial amount of time to get an understanding of that. So, though we are presenting it here as simple as possible, but things are not that easy. So, you have to work out the problems, work out results. So, please try to spend a decent amount of time if you want to get a feeling of the same. Just by reading and listening will not lead you to anything. Listening is important. After the listening you should go back and study that. So, let us start with prolongations. What are these prolongations? Okay. These are called extensions. To have extensions of the functions defined, extensions of function defined on omega. So, whenever you have a domain omega, it is important to quite often you will see that technicalities. In fact, you have already seen the technicalities. Suppose you have a bigger domain omega tilde and a function u is given here. So, can you extend to this portion or can you extend to the Rn, and that extension should not be very arbitrary. Okay. You need to have some control on the extension, okay, not defining something huge. So, you will be as a solution. The advantages is that sometimes near the boundary it will be difficult to work on. So, you need an extended function outside the boundary. So, you get some freedom to work on. And another important thing is that when you extend to all of Rn, you will be able to use the global theory like Fourier transform and convolutions. Okay. The Fourier transform and convolutions are defined on Rn in the full space. So, that powerful theory of Fourier transform and convolutions can be used to extend the function and then conclude about the in the domain. So, the extensions of functions plays a vital role in the analysis of PDEs. But then the extensions are not that trivial. Suppose u is in LP of omega. So, they are looking for trivial extension, okay, any p, okay, and then define trivial extension. We always call trivial extension unless otherwise the trivial extension we denote by tilde. Okay. So, you define u tilde of x is equal to ux in omega and you define 0 outside, that of course is an extension. Okay. And this is called trivial extension, and that immediately can, because it is an additive, the LP norms are just additive things, you can integrations can be added that one and you will get u tilde is in LP of Rn, you see, or LP of omega tilde, whichever be the omega tilde, bigger domain, where the big big domain omega tilde. But this is not true in this is not true for WMP functions in general. Of course, there will be special cases where that trivial extension may work. For example, if you want to see that, you have seen this example, you look at u identically 1, that is in your H1 of 0 to 1, but if you come but the trivial extension, but u tilde is not in H1 of R. The thing is that of course u tilde indeed u tilde is in LP of R, L2 of R, we are working with L2, L2 of R, but you want to see also its derivative, distributional derivative, your u tilde will be delta 1 minus delta 0. That is a Dirac delta, this is not in L2 of R, which you have seen that one. So, the question is that in prolongations, question is that does there exist non-trivial extensions, non-trivial extensions. So, 0 extension may not work, but that is what in the prolongation things does there exist non-trivial extension. As I said, the extension should have properties. So, basically what we are looking is that does there exist linear continuous operator P from, say, let us restrict to H1, okay, it can apply to other spaces as well, H1 of omega to H1 of Rn. So, it is linear continuous, that means you need this estimate. So, the extended function, so what are the properties? And Pu should be equal to u in omega, and that is a very important thing, it is not only an extension and you need to have a control on that. That is what basically the continuity tells you. Pu in H1 of Rn should be bounded by the, with a constant of course, bounded by u in H1 of omega. Okay. So, that means you can control the extended function, but you will see much more than that one. Okay. So, you can apply it to any HM if you want, it is a HM, if you want you can HM. So, whenever you have that one, you have this thing. So, this is very very important to do that one. So, such an extension theorem. Okay. So, the results are there, such an extension exists, such an extension on the case of say H1 exists if omega is C1. This is a regularity on the domain. I will briefly describe you again. Regularity on d omega or omega, does not matter, regularity means inside it is always regular. So, the regularity of a domain means regularity of the boundary. For HM we may need omega is of class, you have seen this in detail in the last class, but I will recall that, class Cm. So, you need more and more regularity if you want to think. Okay. So, in other words you need higher regularity, Okay. All right. So, let me tell you little bit about the so, if the boundary is flat, things are easy. If the boundary, the problem is boundary is curved. If the boundary is flat like Rn plus, I will not you know these spaces, or Q plus, then extensions can be given by reflection, given by appropriate reflections. Appropriate reflection. What is that basically means? So you have your thing here, and this is your, so any point here, this is your xn, and these are all will be using soon, and this will be your x prime xn. Okay, so this is your Rn plus. Okay, this is your Rn plus you have, and this is your x prime 0 identified with Rn minus 1. Okay. So you can reflect the point here, and you get your x prime xn. You can define if a value u is given in say h1 or other places h1 of Rn plus. So it is defined only in the upper half of the plane, but you can define here by defining u of x prime. This is x prime minus n. Okay, x prime x. You see, you can reflect it, and probably sometimes in certain cases you may have to take other signs, etc. But you can do this one to get an extension, and this kind of reflections will not change the H1 norm, because H1 norm of the bottom Rn minus will be the same as Rn plus, and so the total H1 norm will be twice of the norm of the upper half. This is the same thing with your I am doing, because these spaces you will be using it. So this is your Q plus, this is your Q plus, the full thing, and you have your full Q here. That means any point here x prime xn, basically mod x prime is less than 1 and xn positive. So you can do the same reflection here if you and you can define the values. So you can get the extensions in the domain thing. What about general omega? What about general omega? This you have discussed a lot, but let me tell you what. So what's the meaning omega is of type is of class C1. Okay. Let me quickly tell you what it is. So you have your domain here, omega C1 here, and what does it says that, and you have your Q here. Okay. You have your Q, this is your Q, the full domain is your Q. Okay. So for every point you are telling the existence of some map. So every point here, so you can have you this one. Okay. So what you need is a mapping from here, some map Q. So and which should be a bijection. So your existence of a neighborhood you are demanding. Every point on the boundary should have a neighborhood, and this maps is a bijection. So you have your not Q. So Q is already used. So let me use some other map, some other notation. Say G. You have your G inverse. So so basically G is a map from the Q to some neighborhood U. Okay. If so, this is the x point. So this neighborhood here. So there should be an existence of that one. Okay, that neighborhood. So that G is in C1 of Q. G inverse is in C1 of Ux. Okay. So, it is a bijection with that map. So, that you have your thing. And so, if you are saying that omega is of class Ck, you demand G is in Ck, okay, and G inverse is in class Ck. Okay. Extensions are also important to get your some of the density theory. Okay. So, the issue is that you have to, so how do you do the extension? So, you something is given here and this is mapped to, this portion is mapped to here, you see, and then you extend it, you extend, you get extension here, and then once you get an extension you come back here. Okay. So, what do you do finally to do that? So, what you can do is that, so if you have a domain omega, you every point you do these things here like that, and then use your whatever it is called a partition of unity, partition of unity to get an extension to a neighborhood. That is what you do it. By using that thing you can get an extension to a neighborhood. Okay. Once you get a partition of unity and an extension to a small neighborhood, you can do little more using what are called the test functions. You can use some test functions which also we have constructed. What are these test functions? So, you get an extension from u, you get an extension pu, p tilde of u to some neighborhood, okay, some neighborhood, you do that one, and then use these test functions. Test functions are of this form which is identically, not identically one, phi is in, so phi is in d of Rn, okay, and phi identically 1 in some neighborhood of omega, and phi equal to 0 outside some neighborhood. Such construction you can do it outside another neighborhood, Such constructions we are plenty used. So, basically you have an omega here and you have some sort of an omega tilde here. So, here I am recalling this not only for this introduction of this one, so that you will be using it again. So, phi is identically 1 in this neighborhood, and then you choose another neighborhood and phi is 0 here, identically 0. So, you see phi is 0 here, phi is 1 here, and then use that to define your extensions pu, that is nothing but the phi p tilde of u, okay, and that means this is equal to u. So, pu equal to u, because v identically 1, p tilde of u is equal to u inside omega. So, pu equal to u in omega, and it is 0 outside a neighborhood, you see, outside a neighborhood. So, basically you can construct phi extension as small as in a neighborhood, okay. After that it is 0. So, you remaining it is 0, you can't just do that one. From you can extend to some time and then can extend it to be 0. So, you can do. So, these are the kind of things you have to learn, like what is partition of unity, all these constructions of these test functions. So, the one of the important questions you might ask is and that is called. So, if you have a C1, you can do this. If you want to higher regularity, you can't do that. So, that is a definition of C1, you can get such neighborhoods. Okay. Okay. So, the question you might ask is whether Pu, this extended function, retains the W1P spaces. Yes, under these smooth maps you have the change of variable. Maybe I will discuss a little bit about the change of variable. You can actually show that your Pu, if u is in W1P of omega and is of class C1, the extended function u is also the Pu function is in W1. It will not pick up, the extensions are done in such a way that it will not pick up any singularities like a Dirac delta. So, that is our problem. You do not want to pick up, when you compute its distributional derivative, it should not pick up anything which are not functions. One other thing is the Dirac delta type functions. Okay. So, let me do now with this prolongation thing. Now, let me recall a couple of results, not too much, couple of results. Maybe I write it out, density. Density theorems. There are many results. So, two important things I will mention it. So, one result you know, that is the first result which you know is that d of Rn is dense in Hm of H1 or Hm of Rn. That means every function H1 of Rn can be approximated by d of Rn. Use cutoff functions, Fourier convolutions and mollifiers and all that, you have to do that one. The other result, if omega is C1, that will imply you extension, okay, extension operator. Pu in H1 of Rn. I am not going to give you all the details H1 of Rn, but then Pu is in H1 of Rn, Pu can be approximated by d of Rn functions and d of Rn functions can be restricted to your omega. Of course, you will not get d omega functions, but you get C infinity functions. So, so that way in this case for every u, so this you need omega is smooth. So, if u is in W1 H1 of omega, then there exists um not in d omega, but it reaches in d of Rn such that converges to u in converges to u in H1 of omega. So, you see, so you can still approximate your functions via smooth functions. There is a more general, slightly general theorem you for any if domain. So, you are not assuming the smoothness. If you do not assume the smoothness, you do not get these results, but you can still get the approximation inside omega on a convex thing. So, if u is in H1 of omega, then there exists in d of Rn such that, of course, is, since it is a density. So, you get converges to u in LP of omega, but when you have your grade um, it will not you won't get at the boundary. So, you will have your omega converges to grade u restricted to omega for in LP of omega for omega is compactly contained in omega. These things you can use that one. So, the idea is that again use some convolutions and things like that, and the proof of such things you have already think. One last remark in this density theorem, this is actually a more general theorem, probably the proof is much more, is called Mayer's and Serine theorem. Serine theorem, which tells you your h1 of omega is something, it is not that you are, see the earlier functions are C infinity of omega bar. Okay. So, you can use this one C infinity of omega dense in. So, you have dense in h1 of omega. Okay. So, before completing this talk, maybe one last change of variable formula, and okay. So, with the change of formula, a couple of change of formula, I will stop it. This is also important, change of formula, or rather we call it change of variable. A couple of results in this direction, let me call it. So, suppose it is important for you always make a change of variable when you have an integration. So, one domain to another domain when it goes. So, suppose you have two domains omega 1 and then omega 2, then you have a map G here. Okay. So, you want to say be a bijection. Okay. And you assume G is in C1 of omega 1, G inverse is in omega 2, and you also need a sum control on di of Gj, di of Gj and di of Gj inverse consists of some boundedness on its derivative, consists of L infinity functions. Okay. So, it gives you and some derivatives, then the main thing. Okay. One u is in LP of omega 2 implies G composition, U composition with G, right. This will be a function defined on omega 1, this is in LP of omega 1. So, you see under a smooth transformation, it preserves the LP spaces as well as Sobolev spaces. W1P of omega 2 implies U composition G is in LP of omega 1, W1P of omega 2. W1P of omega 2. Once you want to know that, then you also want to know its derivative. So, your dj of U composition G, change of variable formula now, summation, you have di of U evaluated at G into dj of Gi for I equal to 1 to n. So, you have this similar to the classical formula as distributions. Okay. These functions are smooth function, not only L infinity functions, so there is no issue. Okay. There are a couple of more results, maybe I will use a different thing and some 2 results. So, another results, suppose G is in C1 of R. Okay. So, this let me couple C1 of R with G0 is equal to 0, and suppose you have a control on its derivative, that is a derivative is less than or equal to m, and so G is from C1R to R, then U is in W1P of omega implies U composition G, or here anything G composition U is in W1P of omega. So, the space is not changing because G is from R to R, and you have your di of G composition U is equal to G prime. These are all your standard formula. Okay. So, all this you have seen it in some form or other. So, basically you prove these things for the classical formula, use density results to get such theorem. And another thing is a little important, we will be using it. So, suppose G is not smooth, suppose G is only Lipschitz on R. I will tell you one result which we want here with G0 is equal to 0, omega bounded. So, then U is in H1 naught of omega implies G composition U is in H1 naught of omega. Similarly, which you can prove this one. The corollary of this is very important, which we will be using. You take Gt equal to mod T, apply these results, this will imply that if U is in H1 naught, then your U plus the positive part of U, the negative of negative part of U minus U, and mod U, these are all in H1 naught of omega. So, we may use this either during the eigenvalue problem study or some of the situations. U plus is maximum of U0, U minus is maximum of minus U0. Okay. And all that thing. And once the U plus U minus are there, mod U is also in H1 naught of omega. So, these facts, so whatever we are writing this thing we will do. So, we will stop here in this lecture, and we will continue one more lecture on trace theory. We will discuss little bit about trace theory in the next class. Thank you very much.